Well, good afternoon to everybody who decided to join our Sano seminar. Well, today we are in slightly different time zone. We are not in Central European summertime. We are in Central European time. But anyhow, 2 o'clock on Monday is the time for SanoSeminars. And we will start in 2 minutes, I hope. We have almost started, so I welcome everybody who decided to be present at our seminar. And today, as a speaker, we have Filip Katulski, who is PhD student at Personal Health Data Science team. And what he will be talking about today is he will describe his research, which should lead to PhD degree. And for this reason, I would like to invite Jorge Souza, who is the leader of this Personal Health Data Science team, to introduce both Filip and also a topic of Filip's research. So Jose, screen is yours at that moment.
Okay, thank you, Marian. We are, so Filip has a master's degree in computational science and has been working with us for more than 6 months now already. So, and the idea is that we are, as a team, we are developing a couple of components that we aim are going to achieve what we mentioned, what we aim to be computational intelligence. So in the sense that, okay, that we are taking this more cognitive approach of the intelligence in relation to the more connectionist approach that we see nowadays, through deep learning and this generative AI and large language models, very heavily computationally intensive. So we are taking a different perspective on our research, and this is going to materialize into agents, we hope, in the coming years. So, but for that, we need an architecture, and that will be Filip's responsibility doing his PhD, and it's going to be a huge responsibility. No pressure, Filip, on trying on trying to come up with an architecture that will help us to deploy those agents in what we call a distributed AI architecture. So I think that Filip today is going to walk everyone around, what are the challenges, what are the limitations of the things that we have nowadays, and how we think that, this approach can help us to have a different type of machine learning or AI that hopefully is going to be able to continuously learn. So this architecture is one of the pieces of our research that comprise work from other people that will hopefully develop this continuous learning process as an outcome. So Filip is going to show some of the limitations. So, and I think that we'll be more than happy to have some questions, or even me, if you want to ask me some questions, that will be also be fine. Filip, the floor or the screen is yours, and good luck.
Well, just a second. I think that many thanks for clarification and to putting the whole scene where research of Filip he is situated. I would like to just to tell that Filip has completed a year ago his Master of Science degree in Computer Science at HGH University, and it was partially in collaboration with Sano. It was about federated text searching in biomedical literature. And besides of this topic, which was a part of his Master of Science research, he's interested in cloud computing, natural language processing, and also large-scale computing. So, Filip, now floor is yours.
Thank you very much for introducing me in such a nice way. I wouldn't probably do it in such a good way. So let's skip it straight to the details. The topic of this presentation is computational intelligence development towards a distributed continuous learning architecture. And for the next 45 minutes to 1 hour, I'll try to briefly untangle this set of strange and complicated and very sophisticated words to make them as simple as possible to our viewers. Firstly, I would introduce the problem, the methodologies that we take, the hypotheses that we put put here to solve our problems, or research questions that we have. Then we'll present the current state of the art, or at least the things that actually are interesting to me and to my research and to our team. Then I'll briefly say a few things about the proposed architecture that we're trying to develop. Then we'll briefly talk about the test bed, the test environment that we hopefully will use, which is basically our cooperation with certain hospitals in Poland, but more details about that later. Known challenges that we already know that will be major challenges to solve for us, but it's good to know that we know them already. So the conclusions and future plans for the research. So let's start with the motivation. And the motivation came simply in a form of, let's say, set of talks, of interviews with doctors, with medical practitioners, that first of all, doctors and hospitals need tools to speed up and reduce cost of patient diagnosis, because each day doctors let's say, conduct God knows how many different set of diagnoses. They schedule different tests, blood tests, blood samples, and many different computer scans and other type of diagnostic tests to be conducted. And these things cost two things. First of all, time, and time is precious. Time is patient's health, and money, because as we all know, money is always a limited resource, and hospitals really look into reducing this cost of, let's say, reducing number of unnecessary tests. Second of all, the medical data, let's say, if we look at the whole population's data, medical data is spread across many different kinds and sizes of medical centers and research centers. And the idea we had, like, can we somehow distill the knowledge from one center or the other center and spread it across many different participating research and medical centers across the whole system, to give them the information, like, let's say, if a doctor in hospital A do a certain procedure, maybe we could apply it in a hospital B, right? And maybe that will bring some improvements in the process, or maybe cost reduction. And the third thing is, because of certain limitations of how we can solve certain problems, connecting like physically, or let's say programmatically, with usage of IT systems, connecting different sensors, it's already a very hard task. But what we also have to keep in mind is that these are not some random information, not some random data. We are people behind this. This is patients' data. This is sometimes something very private, and something that we should really keep on to secure, not only because it's our legal obligation, but also it's our moral obligation, because we need to keep in mind that first and foremost, we are trying to help people. And we posted a few research questions that we want to solve. And first is how using a distributed system of computational intelligence architecture can reduce diagnosis time and costs, which is a little bit self-explanatory by itself, right? We just want to know how we can implement such a system to actually reduce the time and cost of certain medical procedures, of certain medical diagnosis, and how knowledge gathered from different systems nodes, namely hospitals and research centers, can be shared and used by medical professionals from different centers, right? Because what works in hospital A might also work in hospital B. We might want to share this knowledge, right? And the third one is, can usage of knowledge gained with classification models such as Cactus, which is our tool, our pride and joy here at PHDS team, from different medical centers, can improve diagnosis time. I'll delve a little bit deeper into that later as well. And the hypothesis that we put for the purpose of creating, let's say, a draft of my PhD thesis is that the federated learning provides great results, but requires the training data to be unified and standardized, which may not be possible in real-life medical scenarios. We hypothesize a computational intelligence architecture that provides the opportunity to examine human-like decision-making based on a variety of data sets from different medical centers without sharing the patient's personal data. And I know that's a lot of words, so I'll try to slowly and steadily, with each slide, explain what I meant by crafting this hypothesis. Because we are talking about, let's say, designing a software architecture, first and foremost, what we need to do to actually implement such a thing, we need to apply a set of methodologies, which might be a little bit different and might be a little bit counterintuitive to, let's say, my colleagues who are, let's say, pharmaceutical doctors are focusing about a little bit different things like machine learning, right? First and foremost, we need to conduct a series of surveys, interviews, talks with the engineering staff at our partner centers, because each and every hospital has a different set of hardware, a different set of software. We have different limitations. Sometimes have more rigid rules, some don't. And in order to even actually start drafting the initial idea, we had to just ask the engineers that are already there, like, guys, what do you have? Like, what can we actually build with our stuff, with your stuff? What can we achieve with your equipment, right? The second thing is, because we are building such a, in our plans, this, sorry, Jose, you were trying to say something, or? Sorry, maybe I just misheard something like that. You were just talking. Sorry. Going back to the systems observability, because we are trying to build a huge system, okay, which is in our plans might be quite big. We need to also think about things like systems observability, like all the whole observability engineering side, and think about design also our system about how we can monitor the things that are going inside, so we can always know if something goes down, and if there's some things that we can tweak a little bit and change certain stuff on the go, right? And the third thing is the usability testing. But what I understand by saying usability testing is basically to say that if the doctors actually use the product that we propose them, what do they think about it? What could be the possible improvements? What the IT staff says about maintaining the product that we are trying to propose to them, right? Because it would be great to produce something that it's not only of value on the paper, but also is set with this principle of continuous improvement, and actually it's easy to, let's say, relatively easy to maintain and relatively easy to develop further as our, let's say, demand grows. And because of that, will require all these things, will require a lot of so-called in situ experiments on target infrastructures, because certain problems, we'll know about certain problems only when we start developing our products. There are many things that we'll have to delve into while designing the system, but also while implementing the system. So we also have to focus about that. Okay, and now let me talk about the state of the art, the current state of the art of our system, state of our knowledge that we know about certain elements that I think are crucial. And first and foremost, I had a really great problem with defining what a computational intelligence is. And it's a thing that sounds relatively, let's say, easy to understand. Let's say instinctively we can understand what it means, but I wanted to dive a little bit deeper into what it actually means. And first definition, that I came up with was the definition by not I came up, sorry, I found out, but was the definition by IEEE Computational Intelligence Society, is that computational intelligence is the theory, design, application, and development of biologically and linguistically motivated computational paradigms. It is a very complicated for me. It's not a very simple, straightforward definition, I believe, and I think that some of our viewers might say like, okay, this is just a bunch of buzzwords. So, you know what? Let's just go further and find a different definition, maybe something that will be more self-explanatory, right? And I found a book by Andreas P. Engelbrecht. I'm sorry if I'm mispronouncing the name. The fragment of the Computational Intelligence book. And then it says that these models of biological natural intelligence, these algorithms include artificial neural networks, evolutionary computation, swarm intelligence, artificial immune systems, and fuzzy systems. So we already can say that computational intelligence is, let's say, an umbrella term that basically may actually include many different certain subsets of AI problems that we can solve, like artificial neural networks or swarm intelligence, right? So this is already something that explains to us a little bit, let's say, in form of examples, what the computational intelligence is. Third definition brought up to me by my José Sousa is the definition by Wojciech Duch, is that computational intelligence is a field of, that studies problems for which there are no effective computational algorithms, often because the NP-hard or not they are NP-hard or not possible to formulate. And as far as this is a very good definition, I believe it's still a little bit let's say complicated for, let's say, normal readers. And what is worse, it uses such, let's say, quote unquote hard terms like NP-hard problems, right? What I meant about that is that when we try to explain to, for example, to doctors what the computational intelligence is, they don't always know certain terms that come from, let's say, computer science field, right? Because they're medical doctors, they're not computer scientists. Then I realized that, okay, maybe just let's dive a little bit deeper into, let's say, what the business says about computational intelligence. And I found a company, which is a supply demand optimization company, which they use some software, AI software for the clients. And they provide a a very good definition, which is, I believe, one of the most clear one. That is, this computational intelligence is a branch of artificial intelligence that deals with creating algorithms and systems that can learn from data and make decisions based on what they have learned. This includes tasks such as machine learning, neural networks, and evolutionary computation. Very straightforward definition what it is. However, I do realize this is just a company that just want to sell the products. I'm not judging. That's their selling point, right? But we realized that, okay, maybe we would have to agree on a definition of what the computational intelligence is to us, because as we see with all these examples, and there are many more, that it's not such a rigid definition for everything. We would have to draft our own. And what I will be understanding during this process of developing this architecture is that the computational intelligence is a subset of artificial intelligence focused on continuous learning and inference processes based on free time constraint limitation, which is data that we access, the communication between different nodes, and the computational time. And these computational intelligence mimics human decision making and knowledge gathering, which is, I believe, the most important part. But by computational intelligence, we meant that this is basically a machine or a set of machines that make almost human-like decisions and gather knowledge more or less how humans do. And in my hypothesis, I started with saying that federated learning is such a great tool, right? So why don't we already use a federated learning? And first and foremost, what is a federated learning? I believe that most of our viewers already know more than me what a federated learning is, but let me still reiterate a little bit what it is. It's a technique that utilizes multiple computing, let's say, entities, servers, to train a common model based on the data that is localized. So basically, as you can see, you have two examples of aggregation server model and peer-to-peer model. In this, let's say, left-hand side idea is that we have training nodes, which could be, let's say, our hospital centers, right? And our aggregation node, which could be Sano's facilities. And basically the idea is that the common model is trained on the subsets of data that are spread across multiple different nodes. And then later, during the training process, let's say the weights of the models are aggregated in the aggregation server and sent back for the further training. With a peer-to-peer model, each and every node, let's say, trains and gathers the information about other trainings going on the different training nodes on themselves, and let's say aggregate on themselves each and every one. This is a very good thing that this technique already involves separation of data. And that means that you don't have to share the whole data with each and every node. Each one has just their own subpart of the training. And this is a possibility for a training time and cost optimization, which, as I said, time is a very valuable resource here because we are talking about human lives, right? Because we are talking about patients. We have to remember that this in the back of our head. But the main, and I believe the biggest drawback, is that the data has to be unified across the whole system. That means that the whole data has to have absolutely the same form to even allow our models to be trained on. And that's a huge problem because in real life, as I already said, different hospitals sometimes deal with different types of the medical problems, with different population sizes, with different procedures, even a little bit different from one to another, and data will never be unified across the whole system. It's not possible. Maybe it is possible, but it's not worth even considering trying to unify the whole set of data across all NFZ related hospitals and medical centers. It's just impossible to do it in a relatively humanly time. So we delve a little bit deeper how we can solve this problem, and we came up with a thing which is called multi-agent systems. And I understand that most of my colleagues already probably know much more than me, but maybe we have someone who's outside of Sano or doesn't know that much. So I will try to tell a little bit what I understand by saying multi-agent systems, and what would be the example of our agent in our system. So first of all, a pretty cool definition that I found out is that multi-agent systems consist of multiple autonomous entities having different information and or diverging interests. So for example, in our case, when we are conducting this seminar, my diverging interest is that I want to provide give you a set of, let's say, of examples that we've a set of knowledge that I want to inform you of what I've been doing, and you probably want to just get some get some information out of me. And at Sano, for example, each and every agent would be like each and every employee, each and every researcher, and operational stuff are different kinds of agents, right? And our resources would be, for example, amount of coffee that we can use, and the service and the resources and the services would be, for example, the coffee machine itself, or the copying machine, right? I'm just joking a little bit, but the main idea is that in such a system we have many different agents that might be similar, might be the same, or they don't have to be. What is more important that they operate on having a different set of information and might have diverging interests. And in our case, say the so-called agent in this our computational intelligence architecture would be a local instance of a model job scheduler. I will talk about this a little bit later when I'm explaining the architecture. The graphics user interface that users use to interact with our module scheduler, and many additional tools that will also be necessary for maintaining and operation readiness of the whole system. The so-called knowledge. Knowledge would be the thing that we distill from the local data. So that's why I'm quoting this, because we do not directly have the knowledge about everything. We have to gain the knowledge on something. Knowledge, I believe, for me, it's something a little bit more ephemeral. It's something that more or less exists in human minds, and we are just trying to translate this, let's say, human-like model onto machines. I hope we'll get there. The interactions would be, for example, the results gathering and the knowledge sharing between different systems nodes. The sensing capabilities would be like sensing signals about new records being delivered, new results being acquired from within the system, about what, for example, good sensing capabilities would be that at hospital A, they just realized that at hospital B, they just treated a very similar case that they have had last week, and they can compare the results of the treatment that they both took two different paths, and maybe there's one which is optimal, right? And the acting capabilities would be scheduling model executions and model updates. As I said, I will talk about this a little bit later. And of course, the environment would be the network of the hospitals and research centers. The whole environment would be our medical network. And resources are patients' medical data. And last and very important thing is that the way the doctors treat patients, the way they sort their cases, the way they treat them. That's also, I believe, one of the most important resources, because this knowledge is, let's say, sometimes directly, but sometimes also indirectly ingrained within the medical data, medical procedures that exist. Last simple, let's say, explanation of what I understand by classification models and the algorithms used in computer science to analyze data points and categorize them into different classes. I just briefly want to explain this, that great example of classification model is the decision tree, which we have on the right. And I'm talking about decision tree because doctors, when they saw that there's this concept of a decision tree, they were very keen on this idea that simply drawing, let's say, a tree with different symptoms can give them a certain information that, okay, what's the next most possible path that they should take while curing a patient, right? So if a patient has a fever, if they don't have a fever, he's most probably healthy, right? If they do they cough? If they cough, maybe it's a flu, right? Of course, this is just an explanatory. It's not a real case. Please don't quote me on serving your actual fever and coughing symptoms, please. This is just an example. Okay, and then now let me move a little bit to the proposed architecture. I just wanted to let you know that this is still a work in progress. If you have any questions, please, or any suggestions, which are very welcome, please let us know at the end of this seminar. Sorry, Marian, you wanted to say something?
Oh, okay.
No, sorry.
Go on, please.
No, sorry. I just saw that you unmuted. Sorry. Okay. bestiary, because not each and every one of us is IT guy. So for tools or for tools that I would be, let's say, utilizing the proposed architecture, of course, things can vary, but getting a few concepts behind these icons, these 4 icons I will be using, is a very important thing to understanding the rest of the proposed architecture. The tool called Supabase. It's an open source application development platform. Many of you might know things, which is the thing which is called Firebase. It's a tool developed by Google, mostly for web applications development or mobile application development. This is something similar, but in this case, this is an open source solution. So will not be dependent on Google's infrastructure, right? The Supabase uses because ingrained, let's say, embedded PostgreSQL relational database, and more or less it's self-explanatory. Is PostgreSQL is a relational database that we will be using in our case. But there's also another type of database which is a little bit more interesting. It's a little bit more exotic. Is a graph database called Neo4j. It's a database that allows us to, let's say, embed graphs relations in a form of a queryable set of database instances, so we can directly perform certain how to say it, certain manipulation or certain data manipulations or certain database operations directly on the graphs. And containers, I believe that after a few months with say using Docker, I believe everyone knows what a container is. Container is an isolated package of software with all necessary elements already ingrained within this container. What will be using is a Docker container runtime engine icon just for the simplification. And let us move on. And what I'm trying to present is a very simplistic, very simple bird's eye view on, let's say, 2 nodes variant of our architecture. And we'll be starting with the right-hand side, which is S1, let's say, classification problem. Basically, this agent would be ideally deployed on our partners infrastructure. This is a node, this is an agent, sorry, which main focus would be on providing classification of the local data to the doctors, to the medical practitioners. And what would be including is that for the end device, such as laptop or a computer, or maybe a mobile device even, for a web application, the doctors or the researchers, local researchers, could schedule a certain task, which in our small example is a cactus model scheduler that would run within let's say this whole local environment with the local data of this particular hospital in this example. Of course, this is all a containerized environment. Each and every cactus job is actually a container job that it runs, and then it's in the format it's actually an ephemeral job that it runs, performs certain computations, return the results, and is being destroyed. And within our center, let's say our part of the infrastructure of the architecture, is this classification and rules that we discover and inference on our agent, which would be hosting the whole knowledge gathering part, that the part that actually gathers the nodes, gathers the knowledge, distributed across different databases and data structures that we will create and would be used later for results assessment. And of course, because we are still a research center, we could also perform certain computations on our own and also gather this within our agent. And brief look about how we imagine the process of classification is that the user using this web application sends a certain set of configuration of the model and certain information about, let's say, the environment, where they want to, the environment, the set of data, the problems that they want to solve. For example, they have a patient that comes with a flu, with a high fever, and certain other symptoms, and they just want to get to know from their local data what's the most probable path of what they should do, because the now, let's say, the information about the past cases is already, let's say, ingrained into their local data, so they can try to run a model to actually get the most probable path. And the schedule is in the task. It's being executed within, let's say, ideally within seconds, but probably minutes, right? And the results are then presented to them, and also they're sent to the results assessment of the whole knowledge database, knowledge gathering database. In this model, they could briefly, they have this small loop, let's say, when they can actually take a look. Okay, this is not what I wanted. Let me just briefly reconfigure what I've been asking the system to do, and let's execute this for until I get, let's say, the results that actually are satisfying to me, or maybe change the let's say there's some initial configuration as well, and then get the information that I want. Because first and foremost, we want to help doctors to be as fast as they can in their diagnosis. And this, let's go back to the, let's say, we're going now to this knowledge gathering, let's say, process. And in here, when the results come, first and foremost, that is distributed across, let's say, our structure, that we certain parameters, abstractions, and relations with graphs, or the relations with the different artifacts produced by the models are being ingrained in the relational database. So we know what their basically relations are, right? What is connected with what. The potential graphs that are being produced by models, the classification models that we have, could be stored already in the graph database, so they could be then queried directly. And of course, we need a storage for certain artifacts. By artifacts, I understand that things that do not necessarily could be, let's say, embedded in this traditional relational database, which are, for example, pictures, tables, things that have more, let's say, of a visual value than actual, let's say, table-like values, right? And with each new entry to our knowledge database, whole knowledge database, the results are compared with the old results. So we would know that, okay, with this new case of this specific patient, certain things were done in the past, that we can now see that basically a trending line, that something is being improved or not. And there are some additional agents. And for this, first of all, for the scope of this this presentation, and let's say limited scope of my PhD thesis, there are certain ways that you want to then analyze, for example, knowledge graphs, or analyze the model's analytics itself for the proper improvement of, for example, cactus models. But these things are not the part of my project, so I will just briefly mention that this is the main idea, that we want to gather all this data so we can later provide certain, let's say, data about data for the analytics, for the model analytics. But this is not a part of my PhD, so I'll move on. What we just want to say for sure about the rules describing inference is that during this job scheduling process, we choose different type of an environment that we want to run with the data, the model subtype, because sometimes we have characters model tuned to a very specific set of cases. So, for example, of coronavirus cases, or maybe a different set of cardiovascular diseases. And each and every different model might have a little bit different result. Even if we're using common model, using different, let's say, parameters for the configurations of the same model could give us a little bit different results. So if we're using the same model, but we're using a set of, let's say, different, slightly diverging parameters, first of all, we save the results always. They always have, let's say, history, let's say, a time series of what we've been doing. And then we can select a model with better parameters. That means select a model with which parameters yield better results in the sense of like better accuracy. And then later we can update the scheduler with this information, give us, let's say, in the form of, let's say, information to the user that, listen, the model with set of parameters A, or the first set of parameters, yielded the best results. So do you want to proceed with this exact set of models, the set of parameters? With different models, you have different models. In this simple example, I'm just using Cactus, so it might say my black box that I'm, let's say, working with, experimenting with different models. We always have the results of different models, right? But then we have a thing called a cutoff point comparison, because with classification models we have a certain cutoff point. We need to, at a certain point, we have to decide if the picture presents a cat or a dog, right? So there's a certain cutoff point. And with parameters abstractions, we also have to select this cutoff point to further, let's say, a common denominator, right? And then we can update these models, send this information to the scheduler that we found a new, let's say, baseline for each and every model. So it wouldn't sound like, okay, we have one model that actually talks a little bit more about, is trained a little bit more from the, let's say, Cactus, for example, from COVID cases, a little bit, the other one which is trained with a little bit more data from cardiovascular diseases, and the third one which is absolutely something different, like cancer diseases, right? And each and every model would say that, okay, from patient that has a high fever, he's coughing and he's sneezing, first model will say like, okay, let's say 50% he has a COVID and 50% just a common cold. The other would say like, okay, because he has a high fever and he's coughing, maybe we should try check him for the heart attack, right? Because maybe there's a certain percentage of a chance that there's a heart attack. And the third one would say like, probably it's a lung disease, it's a oncological lung disease, and you have to treat them immediately in that direction. And we're to, in this case, three different models would say three different things, and we want to, let's say, this whole idea of this loop is to find, let's say, a common denominator when the models agree on certain, let's say, edge cases, or certain points that, okay, from this point it might be actually be something more serious, and until this point it's nothing serious. We can treat them more like for a normal flu. And let me talk a little bit more about the computational side. As we said, the three things that are important is data, computation, and communication. Now let's talk a little bit about computation. As I said, we can choose the environment and the data. And as I said initially, hospitals have certain limitations to their infrastructure. Sometimes they don't have that many limitations. They have some a little bit more resources, and sometimes they do. And this might be changing in time. What I meant by that is that one day, let's say on Monday, today, they can run their models on local and fast, let's say, machine that will yield results in, let's say, 2 minutes. But tomorrow, they have to, let's say, perform a certain upgrade to the infrastructure. They have to turn off certain machines, and they only have one small computer usable somewhere, but a 10 years old computer somewhere in the back of their rack that is very slow and would compute the same process within, let's say, 30 minutes. And because of that, it's good to have this, let's say, cooperation with potential HPC centers or any centers that actually, or any resources that are outside and could be scaled outside of organization. But in this case, the problem might be that we are sending, even though anonymized or pseudo-anonymized, pseudo-anonymized data outside of organization, it's still we are sharing the data. So in this case, this would have to be further agreed upon with the hospital, with the research center, with the computational center, and the data could only exist in the form of an ephemeral state when the data is used just for the computational process, and then later everything is deleted and is not held somewhere else. And a little bit more about this communication itself, because how we can, let's say, provide a certain, let's say, more or less safe way to communicate with between different agents. And first and foremost, the raw data with all the personal information is never, let's say, accessed by this architecture, by design. We don't want to deal with anonymized data. We don't want to deal with raw data. What we only want to have is to have anonymized data. So any raw data has to be anonymized somewhere else on a separate set of machines, ideally by the IT staff of the research center of an external research center or the hospital, not by us, because data leakage is a serious issue. We don't want to deal with any potential law problems regarding of accessing raw data. But nevertheless, the anonymized or actually pseudo-anonymized data, because the hospital might want to actually dive deeper into who exactly was the case that we wanted to treat, is never, we don't require the direct transfer to the, let's say, to other centers or to the main, let's say, agent. We only want to share the results, because sending the data, even if it's anonymized, requires another set of different bureaucratic problems and also legal problems, right? Because it's still a form of the data that could be some way retrieved back to people, and we only want to deal with results. And first and foremost, we can set up a VPN tunnel that, let's say, provide this, let's say, very simplistic explanation to how we want to make it a, let's say, a closed tunnel that only specific agents can connect with each other through a VPN tunnel when they can access a specific resources which are hosted somewhere on a virtual machine, let's say, for example, within the another research center's infrastructure. And now let me talk a little bit about the potential test bed, also called test infrastructure. And the test infrastructure would come in the form of our current cooperation with hospitals. The first one is Szpital Tucholski. In English, they have a cute little name, which is Tuchola Hospital, where it's a small hospital in my hometown. Just to let you know, it's a hospital that operates for a population of about 30,000 people. And the other one is a Szpital, is a pediatric, is an allergological and rehabilitation hospital in America. That's their name. Both respective web pages. You can check their web pages. They're very informative about what exactly they are doing. And in our case, of PhD's team, we agreed with Szpital Tucholski that we will implement a pilot program for the pediatric department, because they have around 700 patients per year. It's not a very small number. Remembering that this is just a hospital that operates for about 20 to 30,000 people, and they have very broad spectrum of different pediatric problems, and from common flu, as I said, to some upper respiratory infections, to bowel infections, to some more severe cases. And in America, we have a pilot program in the allergology rehabilitation department for children. And this is much a bigger spectrum, because they have up to 6,000 patients per year. It's a much bigger scope in our case. But this is relatively narrow, relatively in the sense that they don't have to deal with whole set of different problems. A narrow, very specialized set of treatments, allergological treatments, which of course from their perspective is very broad, but from ours it's a little bit different thing. And we already know a bunch of different problems that we'll have to deal with even before we even start implementation. The first and foremost is that the initial system would have a limited number of participants, because as we said, it would be, in our case, would be Sano, 2 hospitals, and maybe 1 or 2 computational centers or other research centers. It wouldn't be, let's say, the whole country. So even though we would have large variety of different medical cases, as I said in the next point, these, let's say, results might be a little bit skewed due to the populational problems. For example, we might have different problems in Krakow than we have, children might have different problems in Krakow than they have in rural areas of Northern Poland in Tuchola, right? And as I said, there are a large variety of different medical cases, and in our system we have allergological problems and also, let's say, more standard infectional problems. And initially that could yield certain problems in terms of, let's say, data analytics that we wouldn't see enough to, let's say, be safe about certain suggestions. Let's say certain things that operate in hospital A would not work in hospital B because the population is different. Different centers have different infrastructures, which is a little bit self-explanatory because there's different hardware, different computers. They even have it's a different software licenses, the different software, different licenses that they have, and sometimes it might be a little bit harder to implement, let's say, one-fits-all solution. It would require a little bit more of a tailoring the initial tailoring the individual agents to the hospital. And that also draws another problem, which is where do we draw the line between the fast and the slow processes? Because as you remember, the computational problems, there might be an issue that for one hospital, something might be a very fast computational problem that could be solved very fast, but the other one might have certain issues with computing something because of lack of proper hardware or software. And how to observe and implement changes and additions in knowledge base that happen across the system, because as we know, things change in time in such an environment. Everything changes in time. Each and every year there's a set of new cases that's, let's say, in some form would update the knowledge base. So how can we implement this addition to the knowledge base that happens somewhere across the system? Which is a very good question, and to be honest with you, I have yet to discover how we can solve this problem. And how can we communicate that new knowledge to doctors? And I believe this is a little bit less than a computational problem. It's more than a, let's say, sociological problem, because sometimes we operate with doctors are humans, and sometimes they might have a certain prejudice, a certain set of let's say, firm path in their mind due to their past knowledge that they already have in their mind, that certain ways are the correct ways, and how can we communicate that there's a new knowledge that emerged from a different medical center that it's worth implementing in your procedures. That's I believe that's a very interesting case, because it's a little bit more about sociology than actual, and psychology than actual computational problem. And to conclude all these things, the initial architecture after, let's say, requirements review from the scientists and the doctors and medical practitioners was agreed upon, and this stage of proposed architecture would meet their requirements if implemented in that way. So the first steps of cooperation with hospitals and doctors were taken. We gathered some data from the wards. We're not in the process of assessing the data and seeing what we are dealing with, what problems could be dealt with. And we already know that there are certain challenges that might slow down the initial implementation process or maybe further implementation process. But the future plan is to find out what we have from the data that we already gathered from the hospital, try to implement the proposed architecture in the environments that we already agreed upon with the hospitals, and conduct some first in situ experiments to see if certain ideas work, or if they're not, I mean, they will require a little bit of, let's say, change, and further development of software components that would be necessary, and of course, publications. Just to let you know, as Marian initially said, I was doing my master thesis together with Sano at AGH University, and this was published. My let's say an extended form of my master thesis was published in the form of a paper in Journal of Computational Science, which is titled "The Next Gen Federated Search Engine for Biomedical Knowledge Repositories, the LitFed Search Engine." You can find it later. I can send it to you, the link. And of course, to be published is the next publication, which we drafted the title Computational Intelligence Development Towards a Distributed Continuous Learning Architecture. And that's all from my side. Thank you.
Thank you very much. Now we have time for questions and for discussion. Well, before other people will start with questions, suggestions, you have presented an architecture with many components. Have you considered instead of implementation of each of the presented components, just let's say building a kind of system of existing or modified candidates for such a components? After all, it is PhD research, not just engineering project.
If I understood you correctly, you are suggesting that instead of starting to, let's say, implement instead of focusing on the architecture implementation, I should focus on, let's say, putting up a set of already existing tools, right?
Yes, just to use to reuse what is already available.
Well, as I said, certain things already are available, and certain things are, let's say, being developed within our team, not by me. So I'm not on my own. Sorry, I just wanted to find us very specific. But yes, some people might underestimate this slide, but I believe it's one of the most important because it suggests that I'm already using, let's say, a certain tools that would, let's say, ease the pain of, let's say, implementing certain solutions from, let's say, software perspective, for the software development, and certain, let's say, components have already been developed by Adam Novak within our team as a part of, let's say, a different project within the PhDS team. So from that perspective, I would be reusing certain objects created already by somebody else. So it's not like I'm starting from scratch. So I know that the time is a little bit, say, time is a limited resource, right? So I understand what you're pointing out, but I'm trying to, let's say, reuse as many components as I can and focus on the problems that we can face further, a little bit more deeper problems, right?
Okay. Well,
Jose, maybe Jose, you would like to add a little bit more about our different components that are being developed by our team.
Well, we have Andrew.
Yes.
Well, I hope that you can speak and be heard.
Hi.
Hi.
I hope that people can hear me. Thanks for the talk, Filip. That was very interesting.
Thank you.
I did wonder, obviously, a lot of these technologies show a lot of potential. Of course, they're sort of complementing what already exists in terms of the clinical process. I'm not a clinician personally, but given that I've looked at some of the clinical processes, my understanding is that the kind of thing you're discussing in terms of sharing knowledge between centres does happen at the moment, but in quite a formalised way, particularly in terms of clinical guideline documents. Now, obviously, they tend to be produced maybe quite a bit behind the current cutting edge literature. So they represent a consensus of groups of clinicians in terms of how best to treat patients. I didn't know if you'd had any thoughts or had any discussions with clinicians. If you could develop such a system, how do you think it might complement or fit in or work alongside those more formal processes? Are there any particular challenges there or any things that you might need to consider even as part of the architecture itself?
Well, let me first start why we choose this option, because well, the doctors, for example, especially at smaller centers, smaller hospitals, they are practitioners. They are not necessarily, let's say, embedded in, let's say, medical world in the sense of a research world. They don't have that much time, and they require a set of certain tools that can provide them results right here, right now, ideally within the time of, let's say, 5 minutes, right? And what we also wanted to have is like a tool that can improve local processes that happen locally in the hospitals. But this was a great point that you mentioned, that also could be a great idea to implement, let's say, some form of a literature, right? As far as that you wanted to suggest that we should also implement a form of like a research literature review for these medical doctors, right?
It is slightly different, because I think my distinction would be research is the cutting edge, isn't it? And research, of course, then is perhaps slightly contentious. You know, the point with research is somebody could publish a new research study, but it may take a number of years before that actually becomes accepted as part of clinical practice. I think the thing, to be very sort of specific about it, what is an interesting perhaps challenge is what happens if a knowledge system starts to recommend outcomes or pathways to a clinician that actually conflict with the current clinical guidance. How is that taken into account? Well, so the point is that I think, again, guidelines, clinical guidelines are guidance, yes. As they say, they're not, a clinician doesn't have to do exactly what the guidance says, but my understanding would be a clinician has to actively choose to go against the current guidance. And therefore, if a system is providing advice that maybe conflicts with that slightly, it would be helpful at least to flag that up to the clinician. So I think I'm making a distinction between clinical guidelines and clinical research, because I think they're two quite different topics.
Well, in this idea, in our idea, we had this, we thought about it like a system that actually, let's say, presents to the doctors what have been doing locally, according, let's say, to the database that they've provided us, for example, for the last 10 years. So any suggestions are actually, let's say, their own work that is being suggested to them, because basically in this case, this system initially would run on their local data, and ideally would suggest like, okay, listen, in your research center you've been doing this, in your medical center you've been doing this, and in the next town they've been doing that, maybe you should do this. We are not doctors, so we are not saying like 100% sure that you have to follow this path. It's up to the doctors to actually decide what they're going to do. So we are safe from the, let's say, from the legal perspective. But well, it's up to the doctor if they are up to date with the current state of the knowledge, right? We cannot force them to be good doctors, right? Jose, I see that you wanted to say something, because I see that you have a raised hand emoji.
Yes, I can explain now, or I can leave it for later. So I don't know what I can the other people to ask.
Go on now.
You know. Okay. Yeah. So good question, Andrew. Thank you for that. Yeah. So we are facing that problem right now. So I have a PhD student that is working on liver, and we already found out that the guidelines for treating lesions in the liver are absent of a lot of dimensions that computational intelligence can give. So we are facing that problem, and that's a problem that we are aware. But here, as Filip said, the humans are, this is centered in the human. So this is just about prospecting and telling, oh, we have this couple of agents that are coming with this consensus about the outcome of this patient or the path of this patient. So, but that's the doctor that is going to say, yeah, yes or no, follow that, or I'm not going to follow the guidelines because I have evidence on that. So, but those we are sure that we have the guidelines that are in place nowadays, as you said, are coming from years of experience and so on. They can be challenged, and that's what we are seeing. So we don't know how that is going to be received by the doctors, but we are facing that right away. But this architecture mainly is to provide a multi-decision layer that normally is absent. So you have multi-decision or multi-layer decision in disease like cancer and so on. So you have to have agreement from different types of expertise. What you are trying to come up is, okay, it's possible to do it for everything. And that's the architecture that we are aiming to deploy.
Yeah, that sounds great, Jose. I'm just particularly interested. I think you raise an interesting point where the output of an agent type approach does actually challenge an existing standard.
Yeah.
And again, I'm using clinical guidelines here as a sort of particular example of that. I think that could almost be worthy of additional reporting or whatever. You can imagine, perhaps if this becomes very widespread, that even that information could be returned to the bodies that develop the standards, yeah, so that if you start to see a spread of practice which is actually moving against the current standard, that would actually suggest that it's an appropriate time to revise the standard. So maybe that's a bit more speculative than the focus of the project at the moment, but I think it's an interesting point. So it's really good to hear that you're looking at that in some of these areas.
So just that's a real thing. So the liver project that I just mentioned, we already found out that, for example, in cases where the treatment is successful, they don't know what to do with the patient. So they don't have a classification process where they say, okay, this patient was successful, and then he needs to be addressed like this. I think that the clear thing here is that if this is a success, is you start having the decision between precision medicine and personalized medicine. So those two things are different and are often confused. So that's what we're trying to provide. You can have personalized precision medicine. Okay, you can target a very specific thing, but personalized medicine is a different scenario. So you have to take a multi-dimensional approach to the patient.
Well, now we have Wiesław in the queue.
Okay, thank you, Marian. Hello, everyone.
Yes, go on.
Yeah, I like the goal of this work. Okay, Filip, you are trying to propose an architecture which is better. Don't thank me; it's too early.
Oh,
Which is better, which is cheaper, which is faster. I believe every doctor will love it. I like your TOC table of content because you said, okay, I present the state of the art. I always like if the work is very well positioned and we know how it's positioned with respect to other works. However, I think that the whole presentation was different story. Basically, the state of the art focus on computational intelligence. On the other hand, something like telemedicine is a daily bread for clinicians. In the US, radiologists are scanning patients overnight. They are processed in India. The next day, there are results for the patients. In Poland, we wait 3-4 weeks or even more. In Canada, there are big networks for stroke because it's a distributed countries and so on, not so many people. So it basically works excellently. There are big projects, international projects working across continents. So people are using telemedicine, people are using architectures, and somehow in your presentation, it's this state of the art, this comparison is missing. On the other hand, you are saying, okay, I have chosen some small local hospital in Tuchola. It might be very nice hospital, but my impression is that you are stating in your goals some global problem, but then you are focusing on some local solution. So how do you feel about that?
Let me start with the telemedicine. That's a very good suggestion to also add, let's say, this form of analysis. You're absolutely right. What I meant by let's say mentioning diagnosis is that sometimes because certain things, because of certain procedures, doctors might schedule a different type of diagnosis to be conducted, to be different, for example, radiology, to a CT scan or a blood sample being taken, where it was not actually, let's say, that necessary in the situation, because they just did it because that's how they should do it. It's a certain code of conduct, right? But when comparing, let's say, for example, historical data at the local center, they could draw the similar, let's say, diagnosis without additional, let's say, without additional diagnosis being scheduled. And as I said, hospitals have to pay for each and every operation. And I'm pretty sure that around 60% of the Poland's population live in the cities and villages of up to 10,000 people. That's most of the people have access to hospitals, which are actually mentioned in my presentation. I'm not saying that it's not like we should also. You're absolutely right. We should also focus about a little bit more bigger scope, maybe bigger hospitals, right? And maybe of course we should draft more hospitals and medical centers into this process. But as I say, this is what we have for now, and this is the hospitals that agreed to cooperate with us. But as I mentioned, most of people, at least in this country, of 38 million, about 38 million, only have access to such a hospital. So it is important to also, let's say, solve problems for everyday John Smith.
But how do you feel that your solution will be better, cheaper, more efficient? You haven't proved it.
Excuse me, sorry, could you repeat, because I'm not sure if I heard you correctly.
You claim that your solution will be better, cheaper, more efficient, but you haven't proved it. You haven't shown any evidence that this is better. Only show the evidence it will be maybe more advanced technologically, but I don't see this clinical efficiency.
Well, I didn't claim straightforward that it's going to be. It is something more better and faster for sure. I haven't. If I said something like this, I'm very sorry. That was not the point. The point is that you're trying to propose something that might improve patients' lives and let's say doctors, practitioners, sorry, life.
So maybe another question. Your perspective is global, or you are looking from perspective of Poland, which we know that networking is not our strength, that, data are really, how to put it, difficult to get. But I don't think so. This is an example, yeah, because again, probably in the Western Europe or in the US situation is much different. So again, how would you position your solution? You are looking for a solution of countries like Poland, or you are looking for global solution which might be accepted globally in other countries?
To be fair, I've never thought about this as a tool to solve each and every country's problems there. I actually, when I was thinking about it, I was mostly thinking about, let's say, smaller, let's say, hospitals in a little bit more remote areas, as the one that provided in this case. I'm not sure if this very specific way that we want to approach things would work, for example, in, let's say, different countries or Asian countries, because I'm not sure about, I don't know anything actually about, let's say, laws about data privacy, data protection, for example, in Asia or Southeastern Asia, right? Or in the US. Actually, I don't know. I only know about how, more or less about how this works in European Union.
Yeah, I would look,
So I would
at
position this about, let's say, as you said, like about problems that solved with countries more or less the size of Poland or some situation.
Yeah, what I was trying to say is that there are countries like Canada, Australia, which really, have a problem that they are a small location, very distant, and they solve it efficiently. So looking at this kind of solutions could maybe help you to enhance your architecture.
Sure. Thank you. Thank you very much.
Okay,
Last
thank
question.
you.
Thank you.
Well, I think that we have on the list Maciek Malarski. Maćku, please go on.
Okay, thank you. Thank you, Filip, for this presentation and the introduction to this architecture. Yeah, I have one small comment about the databases. You have relational, you have graph databases. I don't know if you have looked into vector databases. This is a kind of new buzzword.
Yeah, exactly. That's a new puzzle. But no, I haven't in this for this particular problem. No, I haven't. So I'm very sorry. I would have to review this.
Perhaps, yeah, it could be interesting to see if it fits because actually it's useful for this multidimensional data representations, and you can automatically search for the nearest neighbors, closest points, similarity search. So yeah, something that could be useful for the underlying algorithms, but this is just a small comment. And the other one question is more about what actually also similar to what Wiesław was just asking before. So, this question about is this architecture better, cheaper, faster, etc. So practically, what I would ask is about, what kind of, metrics are you planning to actually use, and what kind of, evaluation, procedures or experiments, perhaps, to conduct to actually evaluate, this architecture, because it's always problems with this kind of software engineering related topics that somebody can see that, okay, this architecture is maybe more clean, more looks better somehow in terms of usability, is more convenient for programmers, etc. But somehow for a PhD research and for publications, it's good to have some simply quantitative measures. So I saw you put some observability there, as one of the points. So it means you are going to collect some information, some metrics, and then so what are these metrics, and what do you want to measure?
Okay,
what to do with these results then?
Well, because we are dealing with, let's say, limited resources, sometimes we might deal with limited resources. First of all, we would have to measure, let's say, how fast a certain, let's say, model execution is, how much time does it take to process this specific data, and make it like analysis of if we actually can allocate more resources for a set of problems, because maybe we deal with this enough resources that we can allocate to our infrastructure. And also, if we have reach a certain ceiling, we can then measure because we don't know what we don't know. So we have to do it, let's say, instead of sort of let's say experiments. First of all, it's like, let's say, like a stress testing experiments when we actually try to max out the infrastructure that we're given to see how many processes we can run, how much and how fast we can process, and if we reach a certain ceiling, how faster it is to send something, let's say, for example, to a HPC center, or I don't know, somewhere else to compute it, than to just wait and make it as a queue and compute it locally. Because as I said, we are dealing with time, and with the time is the main constraint for the doctors, and that's the first thing that I would be focusing on.
Yeah, that's very good approach, I think. But yeah, what I think what you need to also remember is that to identify these constraints, because if you have if we have unlimited resources, there is no point of optimizing anything, but any optimization problem has to have some constraints, and I see potentially some interesting constraints related to limited computing resources in the hospitals, especially if we are focusing on some hospitals that are not in the major larger centers. So this is something worth looking into, and also the costs, but also perhaps some overheads and so on. And also one final comment about that is that it would be interesting to based on this let's say extended state-of-the-art analysis, to find what is the baseline architecture or baseline solution that we compare to, so that we can see that, okay, this old solution or the standard solution that we found gives us such and such costs or time performance metrics, and our improved solution gives us something much better. So this is a kind of general and thank you.
Thank you.
Well, thank you. Wiesław, are you still going to ask a question or comment? Because you have your hands up. Well, anyhow, well, we close the time, which is let's say a kind of a restriction, time restriction imposed.
We still have like 5 minutes,
seminars.
I believe so.
Thank you very much. Many thanks to Filip for presentation and all who decided to take part in discussion. Thank you very much, and I would like to invite all of you to next seminar, which we will have in a week from now, and then it will be Agus Haltoja, postdoc in computer vision team, and it will be about data reconstruction from machine learning models. So thank you very much, and
thank you.
See you in a week from now.